Hello. Everyone hear me all right? Well, welcome. So thanks for coming back to day 2 of PromCon. My name is Bryan Boreham. Let's put that up on the next slide. I work at Grafana Labs. I have worked on Prometheus and adjacent projects for about 8 years now, and I'm a maintainer of Prometheus. But today I'm talking about way down in the hardware, so there's no AI in this talk. There's no demo because I was too scared. In some sense, I didn't really do anything. I mean, well, you'll see what I do. I'm just going to tell you about a thing that you might like to do and what you can do with it. Okay, so well, let's start counters. So I think I'm about the 5th talk to put up a slide like this. Prometheus is pretty keen on counters. And this is an example which is counting how many bytes has this network interface received. So counters are a thing that are found all over the place in operating systems and applications and devices and so on. So yeah, there's billions of them. How many seconds has this process executed on CPU is another popular counter. And that one leads us to CPU is busy. And why do I do this job? Because I basically spend most of my time shouting at the screen like, well, what is it doing? Okay, it's busy. Doing what? The CPU could be doing arithmetic. Maybe that's what you expect, but it might also be waiting for memory. Memory is much slower than the arithmetic bit of the CPU. Or if you kind of understand the complicated bits, that could be the instruction pipeline could have flushed after a mispredicted branch. What can we get that extra level of detail is essentially what this talk is about. So this is CPU. We'll be going through this. No. This is a Intel Xeon Skylake. It is a 28 core, I think. Something that looks a bit like this is a core, and they're kind of mirror imaged as they go across. So that's the kind of hardware I'm talking about. Other CPUs are available. Basically, the same facilities are available on Intel, AMD, ARM. It tends to be on the server parts. Maybe less so on the desktop parts. All right, so this picture is going to be a little bit complicated to walk through, so I simplified it. These are some of the things you find inside a CPU. It's going to fetch instructions. It's going to fetch data from memory. It's got some registers. It's going to read them. It's going to do ALU, the arithmetic and logic unit, and it's going to write stuff back into registers. So, I mean, maybe some of you went to a school where they taught something like this. It's not always as simple as that. I kind of fleshed this out a bit. This is still a very simplified view of a CPU, but there's all kinds of more bits in there. There's in terms of the data cache, there's a level 1, level 2, level 3 caches that go at different speeds. because the memory is like 100 times slower than the ALU. There are multiple ALUs in parallel. We're doing branch prediction, trying to figure out which instructions to decode next. So there's a lot going on. And so basically, the point about counters, CPU hardware counters, is that we can find out what all these different things are doing at what rates. So there is a counter inside the CPU for hits and misses at each level of the cache. And there's more caches here that we'll talk a bit more about later. We've got counts of branches predicted and mispredicted. We've got counts of how many instructions finish this part of the pipeline. So, so that is the basic idea that I'm talking about. The CPU has counters, has a little Prometheus inside it. Does it? Maybe. Well, no. So I've drawn a CPU at the bottom of the picture and a Prometheus at the top of the picture. And we'll walk through how these things connect up. So the first part to talk about is the PMU. So this is a section on the chip. It is roughly there. It's bigger. It's not as big as that in real life, but it's roughly there on the chip. PMU is a term that Intel introduced, but all the other manufacturers are following suit. So you can look for this thing. And the PMU is the part of the chip that's responsible for collecting these counters and making them available to software. On Linux, the subsystem in the kernel that can get hold of these connectors is called perf. The perf subsystem in Linux. Perf is very powerful, very flexible, and so hardware counter is not the only thing that it does, but certainly that's where the counters arrive next in if you're using Linux. And then we need some kind of exporter to get it into Prometheus format. So the first one I'm going to talk about is node exporter. So node exporter already exists. Probably everyone who's using Linux is already running it. But to get it to talk to perf, you turn it on. You say -collector.perf. And this is what we get. Nothing. Okay, why is that? This is what happened when I tried it. I mean, nothing. So it turns out you need permissions to get this information. So basically, you need to tell the kernel not to be so paranoid. The paranoid number is 2 normally, which means it's this much paranoid, and you can tell it to be not so paranoid and let people see the performance counters by changing this sysctl or proc file. Now you can also run node exporter as root, in which case it will have permissions, but then node exporter will shout at you and say you should not be running node exporter as root. So multiple choices how you can do this. If it's inside a container, you might need some other privileges or security profile. Anyway, so I ran node exporter with the collector. We got some data. This is the Grafana drill down view, which I found really nice. It's relatively new. It's like, so you don't actually have to type any promql, but I gave it the prefix node perf. That's up here. So it just kind of finds everything that has node perf in the name and just shows me all of them, kind of grouped and aggregated. So that's great. We got perf metrics coming up on the screen. That's great. Actually, if you look at these, they're not hardware counters. All of these things, context switches, memory faults, CPU migrations, these are things the operating system does. So these are counters that Node Exporter gets from perf, good, but it doesn't get them from the hardware, bad. Okay, what else is going wrong? Why are we not seeing our hardware counters? It's because it's a virtual machine. Virtual machines hide hardware counters. And up until about 10 years ago, this would have been the end of the talk. You know, well, unless you can get hold of one of these things physically. You know, if you buy these things and run the physical hardware, then sure, you can have access to it. But the VMs that we get in the cloud, by default, will hide the hardware counters. And it's kind of a security thing. I mean, basically, you could be renting, you know, 4 cores, and Amazon or whoever would rent you that piece of that chip. And and if you could look at the hardware counters, you could probably tell what other people were doing on the neighboring cores. So that would be a security vulnerability or a privacy risk. And so that's something that never happens. If you're renting a portion of a chip, then you will not see any hardware counters. Nowadays, you can rent what they call metal instances, so you do get the whole chip and no hypervisor. So that's one option. But the other thing you can do is if you rent the whole, nowadays with the modern instances, if you rent the whole chip, then you get hardware counters. So I can carry on with my talk. How would you know? Well, the Intel publish a page. I guess I'll put the slides up somewhere at the end, so you don't have to type in this link. Intel, their literature tends to associate this hardware counters with their product called vTune. But basically, you need the capability. You need to have hardware in this column. So, for instance, an M7i 12x large, that's a 48 core. Well, it's 24 core physical, 48 with hyperthreading. So that one is the whole chip, and you get hardware counters. The slightly bigger 16x large, you don't get the hardware counters because you're actually renting 1.5 chips. So it's a little bit hard to follow, but it's pretty straightforward in the end. So yeah, in terms of demoing for the talk, I took Node Exporter. I rented M7i 12x large, which costs quite a lot of money. Well, because I was doing it private in my own personal Amazon account, so I didn't do it for very long. That's another reason why there's no live demo. Anyway, so now we got many more metrics. This is just running exactly the same command with the paranoid setting turned down on a different machine, and we get hardware counter. So you may be a little bit too small to read, but so we've got like cache refs total. We've got L1D. That's the fastest cache for data. Read hits, read misses. We've got a bunch of metrics here. That's hardware counters coming out at the node level. So that's pretty cool. So tick, we can get data. What if I want more detail? So that's at the whole node level. What if we want to go down to processes or containers? Well, there's cAdvisor. cAdvisor is a project from Google. And I quote, cAdvisor brackets container advisor provides container users an understanding of the resource usage and performance characteristics of their running containers. Does it get me hardware counters? Yep, probably. I just need to give it this -perf events config. I need to give it a JSON file. Okay, how do I get the JSON file? Well, the manual says it should look like this. Okay. Some hex numbers, huh? Okay, cool. I should have asked this earlier, actually. Who's done this before? Yeah. That's kind of, yeah, nobody, right? Just give it a config file. Looks like this. It says config values can be also obtained from a book. Okay, let's get the book. So this is the Intel book that lists all the. This is where you get the hex numbers from. It's a 333-page long book. So each page looks like this. It's excerpt. It's long book because the counters change with each generation of the processors. So they have names like Sky Lake and Ivy Lake and Sky Baby, or I don't know what they called it, but they. So yeah, it's not quite that you have to read 333 pages. You sort of find the processor that you're using, and then you can look up the numbers that you want. As I've said, Intel are not the only people who do this. AMD have a book. Their book is a little bit shorter, but same, volume 2 of 6. Same basic idea. There's a massive book. And you can look up the hex numbers and you can get the hardware counters that you want. So it was a lot easier in Node Exporter, right? I just turned it on and, bit of permissions and I got something. In cAdvisor, I guess it's a googly thing, right? Simply type in the correct set of 50 hex numbers and you will be on your way. Anyway, so there's a but. Doesn't actually work. Wow. So if you download the container image that everyone uses, the sort of whatever Google cAdvisor container, and give it the file with the hex numbers and turn it on, crashes immediately. No waiting. But if you read this issue, people have noted all you need to do is build the software yourself, and then it doesn't crash. So this is on the same machine. I typed in some hex numbers. Actually, so there's a set of things that the perf subsystem can get you by name. So essentially, perf has the hex numbers in it. And then beyond that, there's a set where you have to type the hex numbers in. So this is counting the number of branch instructions, cache misses, instruction, I can get some data out of cAdvisor. And this is at the container level. So we can go down a level. I don't want to go into all the massive depths of how containers are implemented and so on. But basically, if you had a bunch of pods or something like that, you could see them coming out. I wasn't actually running Kubernetes on my machine that I rented to show this with. So the names don't look like. What can you actually do? Is this worth doing? For an example, who knows what the TLB is? Like 10 people? 7? Okay, good. So when the CPU is executing kind of up here. It's dealing with memory in virtual addresses, because you have virtual memory. And then when the physical memory has a different set of addresses, and there's a mapping between them at the page level. So the TLB stands for translation look-aside buffer. That doesn't tell you anything. But the TLB is the cache of mappings from virtual address pages to physical address pages. That's it. It's a cache. If we didn't have this cache, then every single time you accessed memory, the CPU would have to walk the page table. You start with a 64-bit address, and you end up, pages are by standard 4 kilobytes. So that's the last 12 bits are the only bit that actually physically maps into the page. So the first 52 bits of the address have to be walked up in a page table. There isn't a 52-bit lookup. It's a 3-level lookup. You need a cache. How big is the cache? 1,500 entries, roughly. It varies by chip, but that's a good number. 1,500 entries times 4K pages, you get 6 megabytes of memory to party on. You don't use more, nobody uses more than 6 megabytes, right? Surely. Okay. Why am I going on and on and on about this? Yeah, so there's metrics for these things, but they were not turned, or they were not coded into Node Exporter, so I've added them. I don't actually know if this PR is merged yet. Does anyone know? No, okay. So soon you'll be able to run this yourself. So we can get metrics on hits and misses. They're separate TLBs for data and instructions. So this is data hits, data misses. Oh yeah, I didn't put the instructions on this page. This is all data. This is reads and writes, hits and misses in the TLB cache. And what I'm doing here is I'm running a benchmark. I'm running a Prometheus benchmark loading the WAL, the write-ahead log. So this is basically startup of Prometheus. And it's gonna, in this particular benchmark, I'm loading about 8 gigabytes of data. So way bigger than 6 megabytes. So what I'm getting is I'm getting a lot of misses in the cache. I mean, percentage-wise, it's pretty good, actually. The hits are like 1 billion here, and the misses are like 10 million here. So it's actually, percentage-wise, it's pretty good. But I am getting a lot of misses. And what you can do, 4K is not the only choice for page size. You can turn on what are called huge pages, or in Linux, there's a facility called transparent huge pages. Again, I'm not going to go all the way down the rabbit hole here. But basically, if you do this, your Prometheus or your big programs will get 2 megabyte pages instead of 4K pages. They will, so that's 500 times bigger. And we've got the same cache. We've still got 1,500 entries in the cache. So we're going to look up the cache 500 times less, maybe. Okay, so here's the metrics. So I turned on that facility per those instructions, and the number of misses went down. It's me running the same benchmark twice. So that's a concrete example. Given the data, you can tell if you have a particular kind of problem. In this case, I'm getting a lot of TLB misses. Oh yeah, so this is a metric, another Node Exporter metric. This is an operating system metric, but it gave me 12 gigabytes of huge pages, and then it actually stepped down. That's kind of interesting. There's a daemon in Linux that tries to decide how much huge pages you need. It's just running the same metric, same benchmark, like multiple times over. So that's kind of interesting. Anyway, so there was the timings before. It was like 64 seconds. Turn on transparent huge pages and 57 seconds for exactly the same benchmark. So the whole thing 10% faster to start up your Prometheus or whatever. So there we are. That's an example of using hardware counters to diagnose an issue and then reconfiguring the operating system and make your program go faster. So that's the end of my talk.
Amazing. Now everybody knows why I love these talks. Quick question from my side while I walk over. Why aren't huge pages enabled by default on most systems these days?
Right. Why are huge pages not on all the time? So, so basically the amount of memory you're going to use rounds up to the page size. So if you ran a lot of really small programs, then going to the 2 meg pages, you would observe your memory usage would go up massively. And there are some other things that you might not like about it, but basically, so Go actually turned it on. It's either 1.20 or 1.21. The Go runtime folks put some code in Go that would get you huge pages without you doing anything. And they got enough complaints from people who ran a lot of small programs, or for whatever reason, it disturbed their functioning. And so they turned it off again in the .1 release of Go. So like 1.21.1, turned it off again. Those instructions that I quoted are from the go.dev website. So they tell you how you can turn it on and mitigate some of the bad effects. But yeah, it's not on by default. Yeah, make you run.
Hi, thanks for the talk. Do you have anything to add about accessing those counters from Windows?
Oh, Windows. I mean, it's perfectly possible. I didn't take the time to look into that. But I think now you probably got some keywords you could Google. You could do some web search or ask a AI.
Okay, thanks.
Yeah, thank you for the talk. This was really, really interesting. I think the TLB example is interesting because we can control it from the kernel. Do you have other examples in mind, like how you could control, let's say, how many instructions you do? Because I guess a lot of Go developers here say they compile their code, they don't really have insights about how many instructions it is at the end of the day. So,
right, yeah.
And this is a mass of extra metrics.
Yes.
Yeah.
Yeah, I mean, it's a way to get more data, and then interpreting the data then can be its own problem. So in terms of other things you might be able to do with this information, I mean, if you saw a high rate of branch mispredictions, you might be able to reorder the cases. I think the Go compiler is pretty simplistic in terms of how it lays out what comes next, and by swapping around the if and the else, you might get the branch prediction to work better. Beyond that, knowing that you have different rates of L1, L2, L3 cache misses might help you pick a different algorithm or different data structure. That's getting into. I mean, you have to be really knowledgeable about those things to get anywhere. Beyond performance, there are things like security, for instance. So people might remember the Rowhammer vulnerability. So that's an example where you can detect somebody messing around with your system through hardware counters, because that would show up as extremely high rate of memory accesses. Basically, the rowhammer, the exploits would flush the cache repeatedly. So basically never hit even the L3 cache was never hit, and they were hammering the memory. So that's an example. It's not a performance example, it's a security example where you could detect anomalies running on your systems and maybe fire an alert for somebody to go and check that out. Could be that malicious code has got onto your system. Another one, NUMA, non-uniform memory access. That's actually my previous talk from KubeCon Tokyo. But again, they're hardware level counters that would indicate that the chip where the program was running and the chip where the memory was stored were not connected directly to each other. And you could possibly change your config at the kernel level to make that work better. Hi.
You mentioned that virtual machines aren't that well supported because you can't pass down the anonymized information, let's put it like that. But you also mentioned that cAdvisor can split it down on a container level. Are you aware of any efforts on passing down just specific things to your virtual machine instance to the host from the hypervisor?
No, I'm not. I'm not aware of anything beyond. So basically, what ends up happening is the hypervisor itself has a. I don't know if I can get back to the right page. There. So basically, the hypervisor steps in here, and there's what you might call a virtualized PMU. So the code executes a special chip instruction to collect the counters, and that instruction is only allowed in ring 0, so it trips a fault, and now the hypervisor steps in. So your question about could there be better facilities basically has to be solved by the hypervisor. So I'm not aware of anything better than what I talked about. You could go look at the Zen project or their different hypervisors. You could go look at what they support. Or you could ask your cloud provider. I mean, the provision seems to be quite patchy. As far as I could tell, Google Cloud only supports the virtual PMU on ARM chips, so the C4 generation. It's only the newer chips and only some of them. To your question, in theory, the bit of the hypervisor that steps in here could do more, but I'm not aware of any that actually do more. So you guys need to all call your cloud vendors and ask for more.
All right, we're at time. Thank you again, Bryan.
Thank you.